The good news for you is I still haven't put that homework assignment together. I will do it this afternoon. We're having an open house this weekend. There's both green and white days on Saturday, which is mainly for seniors who are looking for, like where to go to college. But then there's an open house here from noon till 4. So that's open to just anyone in the community. And the labs are going to be open. They're going to have food and displays. And so if you're looking for something to do, a cheap date on Saturday, come to the engineering open house. Or if you know, more realistically, if you know somebody who might be interested in the engineering programs or computer science programs, then feel free to send them by. So, getting sort of things together for the open house is in part why I haven't made your homework assignment yet. I guess the other announcement I wanted to remind you about is we're having the alumni barbecue on the 29th of October. That's homecoming. And I'm going to send out another reminder, but I think it's just a great opportunity to network with the alumni, recent graduates, and get a feel for what people are hiring at, or who's looking to take on new engineers. I mean, basically everybody's looking to take on new engineers, but it still might be worth your attendance. And there's going to be catering from Buddies, so free food. So 29th. So keep your eyes peeled on email for that.
They sent it already.
Pardon me?
They sent it to the RSVP a while back.
Yeah. Some people signed up, but not everybody. So I'm going to send it again. Keep hassling you until you sign up. All right, so residuals management. Residual is maybe a euphemism. It's just all the leftover stuff that we actually don't want. And the residuals can come from a lot of different places. Residual can come from sludge that's formed when we are going through the coagulation, flocculation, sedimentation process. And so think about what would be in the sludge coming from a coagulation basin. It's going to, number one, include the coagulant that we added. So it could be ferric chloride or alum. It's going to include the flocks themselves, which is largely colloid particles, meaning like similar to clay, because that was what was suspended in the surface water. But it's also going to be really rich in bacteria, protozoa. So it's not great stuff, not a resource that we necessarily want to try and do anything with, the case of coagulation sludge. Softening sludge is a little bit different. Remember that in the softening process, if we are using the lime soda approach, that it's going to be drawing out calcium and magnesium, both precipitating as carbonates. And so it's going to be a precipitate, which is a mineral, but it wasn't just calcium and magnesium that precipitate out when we raise the pH by adding a bunch of lime. Lime soda softening also was going to be really effective at removing things like lead, arsenic, and so once again we have a sludge that's potentially problematic, that it would be tricky to just dump this sludge into a river, or even just spreading it out over the land. So we have to be pretty well informed on what is in the sludge, because that's going to guide how we dispose of it or how we further treat it down the line. Remember that in the case of sand filtration, occasionally when the head loss increases, we have to go through the backwash process, which is where we're fluidizing the sand bed by turning the flow of the water instead of up to down, which is what it normally does. We send things the other direction, and we're sending water upward through the sand bed to cause the sand grains to suspend, and they start banging into each other and shaking loose the impacted particles. And so that, again, is also going to be rich in tiny little colloid solids, microorganisms, and it can also have things like iron and manganese. Any things that we had pre-oxidized to try to remove. And we talked about how pre-oxidation can cause the iron and manganese that would have precipitated in the distribution network or in people's homes on their laundry. We can kind of target where that occurs, and so ultimately it's going to end in the backwash water. And backwash is a process that maybe takes around 20 minutes compared to, the filtration step could maybe last 8 to 12 hours or perhaps even longer. So, it's not a huge fraction of the water that we're treating, but it's also not just a little bit of water. It's many thousands of gallons each time the filter is being backwashed that have to somehow be disposed of. And there's occasionally ways to try and reclaim some of the backwash water, but there's always going to be a concentrate that has to be disposed of. And the same is true in the case of when we're using membranes. Think about if you're using membranes to desalinate water, and that's what they do, for example, in much of the Gulf region in the Middle East. They either do thermal distillation, or more commonly they use high pressure pumps to force water through membranes that can reject the sodium. So only the water makes it through. So fresh water makes it through, and what isn't making it through is the sodium. And so you have kind of a leftover brackish, briny solution that they have to just dump back into the ocean. And so in the water around a desalination plant, the salinity is actually elevated, because what they'll do is they'll bring in maybe 3 gallons of seawater, produce 1 gallon of fresh water, and they're discharging 2 gallons of leftover water that was washing over the surface of the membrane. And then also they're mixing in the additional sodium that got rejected with the 1 gallon of fresh water. So you're getting all of the leftover minerals, in this case that I've been explaining, just sodium, but membranes can be used to remove a lot of different things. If you're trying to use a membrane to prevent arsenic from getting into the water, then you end up with a concentrated arsenic solution. And so whatever it is you're trying to filter out to not send into the distribution network towards people's homes is going to accumulate into a waste stream. Ion exchange, the most frequent use of ion exchange is at the point of use where people have water softening in their homes. And so the residuals there is the fact that every so often the ion exchange resin has to be regenerated by sending a concentrated sodium solution, because what we're doing in ion exchange for softening is taking the magnesium and the calcium out of the water and replacing it with an equivalent charge of sodium. And so every once in a while we have to put more sodium back into the resin, and so we flush it with a really highly concentrated brine, and not all of that brine, not all of the sodium ions go back into the resin. So you've got this backwash that's very salty and also has a lot of calcium and magnesium in it, and it's just usually sent to the sewer. And so each one of these different steps is generating a waste. Now, sludge is going to be something we're concerned about both in water treatment and in wastewater treatment. It's a mixture of solids and liquid. And we can break solids down into some additional categories. There's the fixed solids, meaning minerals like calcium carbonate, magnesium carbonate, and so on. Alum is another mineral, ferric chloride. The minerals are things that wouldn't burn away if we lit this sludge on fire. They're fixed. But volatile solids are organic materials that would potentially burn away. So it could be microorganisms in a drinking water sludge. In the case of wastewater sludge, there's a lot of organic material there because people put, of course, food waste and human waste, and all of that can be burned away since it has a high carbon content. But our textbook goes through a series of equations that we would need to help do calculations related to the volume and the mass of sludge. And this is a huge concern. It's a really big part of the cost of drinking water and wastewater treatment is disposing of these residuals. You think about how treatment plants are spending money. They're spending money on electricity because they have to move water from one place to the other. They're using electricity for things like blowers. In the case of wastewater, you're aerating activated sludge, but even in drinking water, we're using blowers for things like air stripping of carbon dioxide, air stripping of harmful volatile organic constituents. So electricity is a big part of the cost of drinking water treatment. Of course, there's labor, there's chemicals. We're having to pay for things like lime, other pH adjusters like excuse me, sodium hydroxide. During recarbonation steps, that's a chemical cost, alum, lime. But a big part of the expense of drinking water treatment is just disposing of the sludge. And one of the ways that you can cut costs is by concentrated sludge. Because the typical sludge is only just a tiny fraction solids. It's mostly water. Like a typical sludge would be 98 or 99% water and only 1 or 2% sludge before it's thickened. And if you can double the solids content, then you're cutting the volume of sludge in half. And this is a little bit, it's not something that would immediately occur to you, but a sludge that is 1% solids is going to occupy twice as much space as a sludge that is 2% solids. It doesn't seem like a big deal going from 1% to 2% solids, but if you do that, you're cutting the volume in half if the mass of sludge solids is the same. And we'll go into some calculations that kind of make that point and illustrate. But this first formula just shows how the mass of sludge solids is a combination of the fixed and the volatile components of sludge solids. Now, specific gravity, in fluid mechanics, we sometimes abbreviated it as SG, is the ratio of the density of something to the density of water. So it could be another liquid. If we were talking about the specific gravity of oil, then we would find the density of that oil relative to the density of water. It doesn't even have to be a liquid, though. It could be the density of some solid particle relative to the density of water. So if you know, for example, that a certain sample of clay has a density of 2,600 kilograms per cubic meter, then you could find the specific gravity of that by having the 2,600 kilograms of clay per cubic meter divided by the 1,000 kilograms of water per cubic meter. So specific gravity is a unitless ratio. That's just the density or the unit weight of something relative to the density or unit weight of water. So if we know the mass of solids, the density of water, and the specific gravity of the solids, then you can find out the volume of the mass of solids. Now this isn't the sludge volume. This is just the volume that the dry solids occupy. So it's really the sludge volume that we're more interested in, but this would allow us to calculate, ideally, if we could squeeze all of the water out of these solid residuals that are being formed, how much space would it occupy? So it points us towards an upper limit of efficiency and the volume that would have to be removed. So I've told you already that most sludge is just a tiny fraction solids and mostly water. So if you can do something to remove the water, like drying the sludge or thickening it through gravitational effects, or there's some pretty interesting things people do to thicken sludge. They'll freeze it. Sometimes by freezing sludge, it allows the solids to settle out more completely in gravity. Sometimes they'll electrify the sludge. It's like torturing the sludge to try and get the water separated from the solids. Putting it through a filter press is one approach. Let me dim the lights a little bit. Yeah, so this is kind of like, have you ever been to a football stadium where they have those, like a roll of towels? Those always kind of give me the creeps a little bit because it's like, I mean like the fabric towels that recirculate through. Some people are giving me a quizzical look like they've never seen those before. You've never been in a bathroom where it had like a fabric towel? Wow. You guys need to get out, see the world. Go see some more football stadiums or something. I mean, it's not as common as it used to be, but, you know, yeah, so, huh? Oh, I guess I got to Google this, right? We got to, okay. Yeah. I'm too cheap for that. They charge a lot at football games. Fabric hand towel dispenser. All right. This is, yeah. So it's basically, it's fabric, and it goes down, and then it goes back in. So, what they usually do is I mean, you're not, it's not just like a single loop. I mean, it's not like 5 feet long. Inside there, they've got it rolled up tight, and so it's supposed to have thousands and thousands of feet. Well, I don't know, thousands, but more than just like a single loop. So hopefully you're not drying your hands off like what somebody else already has, but it's a closed circuit towel. And so is the filter press. It's a closed circuit towel. So they've just basically got this conveyor belt above which they are suspending a piece of fabric and some rollers. And so the sludge goes in one side that's a little bit opened. They're feeding the sludge in, and then they're squeezing it, and they're pressing it. Have you ever tried Greek yogurt before? Greek yogurt is just normal yogurt that they take a normal can of yogurt and then they pour it over a piece of cloth. And some of the water gets through, and once they've extracted a certain amount of water out, then they take the rest and then they just put it in another container. So it's just they've strained regular yogurt to get some of the water out. And so they're doing a similar thing here. They're taking this wet sludge, they're putting it through a fabric that kind of, there's a top and a bottom layer that squeezes it together, and what comes out is much drier than the sludge that went in. And the water just drips down through the bottom.
Dr. Witt, I don't like all these comparisons you're making to things we clean our hands with,
Yeah.
our hands off with and eat.
Yeah.
Sludge.
Yeah, you're supposed to go to lunch next, and all this talk of sludge is ruining your appetite. But you're going to have to really get hardier because we're headed into the wastewater treatment section of the course. So you may want to eat before you come to class, starting in a couple of weeks. Because things are going to, we're just talking about drinking water treatment now. It's about to get a lot grosser. All right. But you get to a point where the smell doesn't bother you. I guess if like you're a cattle farmer, the only thing, like when I go to a wastewater treatment plant, the only thing that's not great is the bar rack. Yeah, the bar rack's the first thing that, I don't know, the rest of it's okay, but the bar rack's pretty bad. All right. Another way to thicken sludge, it's called dissolved air flotation. And this is a pretty interesting technology where what they do is they'll take a dissolved gas, it may be CO2 or just it could be ordinary air, dissolve it into solution, and then they inject it at the bottom of a chamber, and the bubbles float up. And just think about like when you open a can of soda, the bubbles float up, and if you had a sludge in this, the bubbles carry the solid particles up towards the top. And it forms a blanket at the top because the bubbles are pushing up from beneath. And so once the sludge gets to the top, then there are these little wipers that scrape it from the surface and put it into a trough, and then what comes out is a thicker sludge into the hopper. So it's just another way of using differences in density to separate the liquid from the solid, which is kind of interesting because normally the solid particles are going to be more dense than water. So more common is to use gravity to thicken sludge. You just put the sludge into a tank that you can leave it for longer, and the solid will settle to the bottom and the liquid will rise to the top. But you can use this dissolved air flotation as kind of to flip things around the other way. Instead of having the solid particles go down, you have them go up. This table from our text illustrates some achievable solids concentration from different types of technologies. Another one that I didn't show you a picture of is using a centrifuge. So, I think that's probably pretty obvious to you that if we had a test tube like this, we could spin it around in a centrifuge, and because there's a difference in density between the solid particles and the liquid particles, the solid would settle down to the bottom. So it's a gravity settlement using similar to gravity, but if you want things to go faster, then you just give it a greater acceleration than gravity by spinning it in a centrifuge. There's also vacuum methods where you're trying to enhance the straining effect by sucking the water out of the sludge with a porous stone on one side and a vacuum on the other. But if we look at the maximum range of these, you can get sludges as high as 60-70% solids, although I think that most treatment plants balance the cost of disposal with the benefit of decreasing the volume of the sludge. And so, if you don't have to pay too much for sludge disposal, then it may be good enough to take the sludge to 25% solids. But if you live someplace where environmental regulations are really strict and landfill volume is really expensive, then it may pay to really invest in water reduction and sludge thickening. Okay, so sludge volume is important for us to be able to estimate. And there are some empirical relationships I'll show you in a minute that allow us to estimate the volume of sludge for alum or ferric chloride addition, or even for softening reactions where we're trying to figure out how much calcium and magnesium have been removed. But just to start off, we want to know the fraction of solids relative to the overall mass of sludge and the fraction of water relative to the overall mass of water. So don't worry about taking down all of these definitions, because I think if you look, you'll see it's pretty self-explanatory. It's just saying the mass of solid divided by all of the mass, which is to mean the solid and the water. So that's just going to be the fraction of the solid compared to the total. And so then the fraction of the water is the mass of the water divided by the total mass. There's no heavy lifting yet in either of these formulas. This is a little bit more interesting because this is what we could do to estimate the specific gravity of the sludge. So we want to know, how does the density of the sludge compare to the density of water? And that would help us to know maybe which treatment technology to use for the dewatering. And it's certainly going to be useful to calculate volumes. So you can see that we need to now know the specific gravity of the solid particles. So the solid particles could be colloids, it could be the precipitate of calcium or magnesium from a softening reaction. And then finally, here's the formula that would allow us to estimate the volume of sludge. So let's try using this in the following example. we took a sample of sludge that was 800 milligrams, and in the 800 milligrams there was 31 milligrams of solids, and then the rest of it is water. So the water mass in that sample would be 800 minus 31. So with this first sentence, we can find out the fraction of solids, the fraction of water. Now it also tells us the specific gravity of the solids in the sludge is 2.45. So that is this S sub S, the specific gravity of the solids. So remember, the sludge is not very much solids. It's mostly water. But of those few solids that are in there, the specific gravity is 2.45. Now we're at a location where we have 275 kilograms per day of solids that are being generated through softening. So let's try and estimate what will be the sludge volume if we know that the mass of solids per day, M sub S, is 675 kilograms per day. And you're going to need to calculate P sub S and the specific gravity of the sludge. Because I want to reserve some time for the other example, let me just jump ahead and show you the solution to this one. Even if you haven't maybe finished it up yet, we can check to see if you were headed in the right direction. So we need to identify the mass of solids, the mass of water. So the fraction of solids is 0.03875. Now, why do they use the P? But I guess you could think of it as a percent. It's 3.875% solids. But it's expressed as a fraction. So they don't explicitly say it's a percent because it's expressed as a fraction. The specific gravity of the solid is 2.45, and that, along with the fraction of water, is going to allow us to calculate the specific gravity of the sludge. Now, it should be pretty close to 1. If you get anything really far away from 1, then you may have an error. And the reason why is, this sludge is 96% water. And so it's going to have a specific gravity that's pretty close to water. So the specific gravity of water is 1, because that would be the density of water divided by the density of water. So here, the reason why it's 1.023 is because most of the stuff that's being averaged, like we're averaging the specific gravity of water and the solid particles. And so it's only 3.8% solid particles and 96.1% water. So that's why the specific gravity of the sludge is so close to 1 there. Now, once we have that, we can estimate the daily amount, the daily volume of sludge that's going to be generated, because the mass is 675 kilograms. So how much space is that going to occupy if we're generating 675 kilograms of sludge each day? Well, it's going to be the 675 kilograms divided by the unit weight of water, and then the density of, the specific gravity of the sludge multiplied by the fraction that is solid particles. So it's going to occupy 17.02 cubic meters. Okay. So that just gives you a feel for how the pieces fit together. Any questions on this first example? Okay, this is an empirical equation that allows us to estimate the mass of dry solids that are going to be recovered when you have a sedimentation basin downstream of alum coagulation. And so what you can see is that we have some conversion factors built into the formula. Like the 86.4, does that seem familiar to anybody? Yeah, that's related to the conversion of seconds to days. And the reason why it's 86.4 and not 86,400 is because we're going to put in concentrations in terms of milligrams per liter and get kilograms out of the formula. So they're combining both the milligram to kilogram conversion and also the seconds to days conversion in this 86.4. So what you'll do is you put the flow rate Q of the treatment plant. So that's how much water they're treating each day. And then you have to know the dose of alum that's used and multiply it by 0.44, because for every milligram per liter of alum that's added, you're only going to have settled out 0.44 milligrams per liter of sludge, because the alum comes mixed with other things that aren't precipitating out after settlement. Then also you would be removing the suspended solids. That's why we added the alum in the first place. And then any other miscellaneous things that might have been added to help improve the bulking ability of the flock. So if we're adding any polymer to improve the settleability of the flock, or sometimes they'll mix in powdered clays to try and give like a nucleation effect to the flock and help it to settle more quickly. All of that is presumably going to be settled out and is going to add to the mass of solids. There's a similar formula that applies to ferric chloride. And the interesting thing to notice is that you're going to be generating a lot more sludge with ferric chloride than you do with alum, just by virtue of the chemical reaction. And so this is another balancing act that designers have to take into account: the relative cost of alum to the relative cost of ferric chloride, and then the cost of dewatering and disposing of sludge, because ferric chloride is going to be generating a lot more sludge than alum does on a gram per gram dose basis. There's a similar approach that's taken to estimate the effect of softening. So this is for coagulation. If you are doing lime soda softening, then the amount of carbonate hardness that's removed goes into the effect here, a calcium carbonate hardness, the amount of magnesium carbonate hardness, non-carbonate hardness if you're doing soda addition to try and remove non-carbonate hardness. So all of the contributors to the accumulation of sludge during a softening reaction are taken into account given relative weights, and then we multiply it by the same 86.4 to both convert the milligrams to kilograms and seconds to days. So this would give you the mass of solids that are being generated. And let's see, we've only got 3 minutes left, and so unfortunately I'm just going to have to show you this example that I had in mind. We had a sludge that we knew was 3.875% solids. So that's the value from the last example. And we've got a certain specific gravity for the sludge. What if this was at a water treatment plant that treats 10 million gallons of water per day, and then we also know that they're doing softening, and so they're removing some carbon dioxide, they're removing some calcium carbonate and magnesium carbonate, but they're not removing any non-carbonate hardness. They're just doing lime addition to remove the carbonate hardness. So what we have to do to figure out the volume of sludge is, first of all, find out the mass of sludge that's being generated, m sub s, and then substitute that into the volume of sludge equation. So let me show you just what that looks like. We already knew the percent solids is 3.875. We're given the concentration of hardness that's being removed for magnesium, calcium, and carbon dioxide. Converting 10 million gallons per day into cubic meters per second, because that's the format that we need for Q. So then with that, we just substitute in all of the different amounts of hardness that's being removed, and we can estimate the mass of solids that are being removed each day. So this would be about 20,000 kilograms per day of solids, and that's about 42,000 pounds. That's half a truckload. So that's all I've got for you today. I will be putting homework 5 together, and you'll have it no later than Friday. So I will see you then.